Welcome to bolivartech.com. CuaimaCrypt, a strong cryptographic alternative. CuaimaCrypt is a cipher designed by Julian Bolivar-Galeno in 2007, with improvements suggested by Jonathan Pastran during the development period. CuaimaCrypt originally had two versions, CuaimaCrypt Stream Codec or CuaimaCrypt SC, which was designed for hardware implementation, making encoding data streams in real time, and CuaimaCrypt Block Codec or CuaimaCrypt BC, which was designed for software implementation because it uses the capacity of PCs to process data blocks efficiently. Currently the most distributed and used is the CuaimaCrypt BC, and I will focus this article on it. Traditional cryptographic algorithms such as AES, RC4, Blowfish, DES, Triple DES, Serpent, Twofish, and others, have predetermined fixed structure. CuaimaCrypt has a dynamic structure. Due to this, the structure is unknown in advance, only the basic layout is defined. The CuaimaCrypt structure is determined based on the key used. This feature, together with the coding blocks operation, makes it more robust to cryptanalysis than traditional algorithms and current quantum computer attacks resistant, as was exposed in my other article. NSA believe that current cryptography algorithms are broken by new quantum computers. The CuaimaCrypt's heart is the shift codec and shift decodec, who are those that allow the encoding and decoding the clear data. The shift codec consists of a 64-bit shift register, 5 32 bits XOR gates. Also it has two internal 32-bit windows, identified like win A and B, and a shift leap parameter which determines how many bits are going to be shifted by the register at each iteration. Another important point is, the shift codec have a up chain and down chain, which are linked to other shift codec in CuaimaCrypt's structure. Also in the shift register are defined two anchor points, up chain and down chain, from other two shift codec in CuaimaCrypt. The shift decodec has an identical structure to the shift codec. The difference between the shift decodec and the shift codec is the feedback point for the upper loop, which uses the clear data to feedback the loop. This is very important for the system security due to two reasons. The first is that in order to decode data at time t plus 64 divided by shift leap must have successfully decoded the data at time t, otherwise the outcome data will be useless because the system will diverge from the original sequence. The second is, with this feedback the shift register does not suffer from the drawbacks of linear feedback shift registers or FSR, which the problems of sub-cycles or shorter cycles. Due to the feedbacks loop, the up and down chain connections, the shift leap and the dependence of the clear data, the shift codec and shift decodec not have cycles that can be predicted by cryptanalysis. The shift codes and shift decoder form a mesh using the up chain and the down chain. Each connection up chain and down chain are bind to a single shift codec or shift decodec, but not necessarily the same, and each shift codec or shift decodec can only receive an up chain and down chain, so the connections are unique among shift codec or shift decodec. Additionally, the connection point where is extracted the shift register's data is dynamic. These connections must be initialized before start coding and must be key dependent. The shift leap is a parameter that defines how many bits are going to be shifted in each cycle. This value is between 1 bit and 15 bits per cycle. The rake codec and the rake decoder are formed by grouping 4 shift codec and 4 shift decodec respectively. This group of shift codec and shift decoder can process blocks of 128 bits. The byte scramblers are functions that combine the 4 32-bit outputs form the rake codec or rake decodec. These are used to increase the coding's entropy as it mixes the most significant and the least significant bytes. The interleaving is used to make orthogonal the input data using a Walsh code in order to produce an equal distribution of 1 and 0 in the data. It makes a mixture of the most and less significant bits. The scramblers and the interleaving help to produce a flatter distribution of values over the ASCII table. CuaimaCrypt in its most basic form is formed by interleaving the input data, 2 blocks rake codec and 1 scrambler between rake codec. One of the strengths of CuaimaCrypt is that this structure could be repeated almost indefinitely, depending on available memory and encoding rate required to increase the level of security required by the application. At the present, for the Valhalla's most classified documents, we are using CuaimaCrypt with 512 blocks. The CuaimaCrypt's initialization is set using the following parameters: number of blocks, seeds of shift codec, sequence of scramblers to be used between blocks, hopping sequence between shift codecs, up chains on each shift codec, down chains on each shift codec, start point window for each up chain shift codec, start point window for each down chain shift codec, start point window for win A in each shift codec, start point window for win B in each shift codec, shift leap for each codec, Walsh code to be used in the interleaving. The initialization process can be performed by any method chosen by the programmer using the library, but to determine the security of the algorithm is imperative to be very careful in the way to implement it. At the valhalanetworks implementation, to initialize CuaimaCrypt we are using Lorentz attractors. The Lorentz attractor is a concept introduced by Edward Lorenz in 1963. It is a three-dimensional deterministic nonlinear dynamic system derived from simplified equations of convection rolls that occur in the dynamic equations of the atmosphere. For certain values of the system's parameters, it exhibits chaotic behavior and show what is now called a strange attractor. W. Tucker proved in 2001, the strange attractor in this case is a fractal of Hausdorff's dimension between 2 and 3. Grasberger at 1983 estimated the Hausdorff's dimension in 2.06 and a correlation 2.05. In order to perform the CuaimaCrypt's parameters initialization, the Lorentz attractor are used to generate a pseudo-random sequence difficult to determine without knowing precisely the starting points that was chose. To determine the CuaimaCrypt's security level is necessary to establish a comparative framework which should be equivalent to that used by other encryption algorithms. CuaimaCrypt's operation is different and is necessary to determine a key length equivalence that include all the CuaimaCrypt's initialization process. The equation that define the possible combinations of CuaimaCrypt's configuration is n powered to 5 multiplied by n minus 1 factorial powered to 3 multiplied by 2 powered to 258 n plus 29, where n is the number of blocks in the algorithm. For the case of n equals 2, this equation result is 3.6855 multiplied by 10 powered to 165, which is equivalent to 550 bits. For n equals 4, this equation result is 5.4648 multiplied by 10 powered to 324, which is equivalent to 1078 bits. For n equals 6, this equation result is 7.1220 multiplied by 10 powered to 484, which is equivalent to 1610 bits. For n equals 9, the equation results 2.0384 multiplied by 10 powered to 726, which is equivalent to 2412 bits. For n equals 16, the equation gives a value of 5.6466 multiplied by 10 powered to 1293, which is equivalent to 4297 bits. For n equals 32, the equation results 2.0153 multiplied by 10 powered to 2603, which is equivalent to 8647 bits. For n equals 64, the equation results 1.8187 multiplied by 10 powered to 5250, which is equivalent to 17440 bits. For n equals 128, the equation results 8.2660 multiplied by 10 powered to 10,600, which is equivalent to 35,215 bits. For n equals 256, the equation results 5.9661 multiplied by 10 powered to 21,416, which is equivalent to 71,144 bits. For the security scenario of n equals 512, the equation result is 4.2701 multiplied by 10 powered to 43,278, which is equivalent to 143,768 bits in a classical cryptographic algorithm. For the extreme security scenario of n equals 1024, the equation result is 4.6637 powered to 87,463, which is equivalent to 290,548 bits in a classical cryptographic algorithm. In perspective, at the observable universe we have in a gross underestimation of 1 powered to 29 stars. If we compare these values with known symmetric key algorithms, we can see, AES has 256 bits, Blowfish has 448 bits, Ghost has 256 bits, Redoc has 160 bits, IDEA has 128 bits, MMB has 128 bits, Cypher K128 has 128 bits, New DES has 120 bits, Three-Way has 96 bits, Crab has 80 bits, Skipjack has 80 bits, and it is a classificated algorithm by the NSA. Cast has 64 bits, Madriga has 64 bits, FEAL has 64 bits, Loki has 64 bits, Cypher K64 has 64 bits, DES has 56 bits. CuaimaCrypt is a mature algorithm with 9 years in the market without any, reported or known, security fails at valhalanetworks implementations. If you want to try a powerful implementation of the CuaimaCrypt algorithm for all platforms, just please visit CuaimaCrypt command line or CCLI at valhalanetworks website. Thanks for watch the video, and you are invited to subscribe my channel. More interesting contents available at bolivartech.com, and please follow me at my social networks.